quantum tunneling in breather nanocolliders. I'm a fresh guy in this community. For 30 years I've been doing solid-state physics research, and my first paper on the subject that was published just last year, and another one is available on the archive. And from the literature and from this conference, I understood that in spite of the vast majority of very convincing experimental data, the comprehensive model of linear still doesn't exist. And so my goal today is to present you such a model. I understand that this is a bold statement, and even maybe bold it will seem to you to hear that I think, and I will try to demonstrate to you, that to understand land, you don't need to invite conceptually new physics. What the physics already done for us is enough. Here's my co-authors. One of them, the top guys are from Belgium Research Center, who do the molecular dynamic simulation for radiation damage studies. Below are professors who real experts in the non-linear phenomena in solid-state physics and in organic materials. And actually this topic, non-linear phenomena, will be the key topic for today's talk. We all know the main requirements which should be explained by a comprehensive model. These are, of course, high loading, which is more or less understandable, yes, and external driving, which concerning, of course, the electrolysis conditions. And up to this external driving, we don't yet have any convincing explanation. Of course, the main problem with the linear is how to get through the Coulomb barrier. Tunneling coefficient, by famous Ganov formula, is extremely low for low temperature in solid state. It's so low that the life of universe will be not enough to surpass it. So what is it? Screening, the most popular model probably. But you see that dependence on this tunneling distance is extremely strong. It goes from 10 to minus 100 for the distance of about 1 angstrom. And if we even introduce the screening potentials taken from these beam experiments, yes, from palladium or platinum, we will see that it's far not enough. And actually they measure wrong reaction because they measure proton yields mostly. And in real LNR, we don't measure any particles. So I would say that using accelerating ions for studying LNR is approximately the same that using hammer for repairing watches. Of course you can break watches, but whether you understand how they work. Our question is how absorption-desorption reaction couple energy into modes of lattice vibration appropriate to stimulate DD interaction. This question has been actually posted by Mike McGilvray more than 10 years ago, and it still goes unanswered. One of the attempts were to couple these two lattice vibrations, which are described in phonon language. Phonons, the problem is phonons that are essentially delocalized quasi-particles, and actually it's not actually quasi-particles. They exist only in our heads. In reality, atoms represented by phonon modes just perform very stochastic, very small amplitude, about 0.01 angstrom, which is not enough. And attempts to correlate, for instance, the influence of laser beams on the excess power output are very interesting, but as I will show you later, they have different explanation. And this explanation lies inside this new field, which we call this nonlinear phenomena, and here we introduce a new quasi-particle, real quasi-particle, which is called discrete prism, localized, large amplitude, anharmonic, atomic oscillation, which can be excited outside phonon bands, which is very important. Now I will show you first the simplest example for one-dimensional Hirota lattice model. It has exact solution. It looks like that. Look, this is a weakly and strongly localized discrete prisms oscillating with a frequency lying above the phonons. It's not a cartoon movie. It's a strict, exact solution to these nonlinear coupled equations. Yeah? And what is, if you look at the right, strongly localized picture, you will see that the central atom oscillates with a huge amplitude. We will see it will be about 0.3 angstrom, while two adjacent atoms oscillate very weakly, but with the same or with coherent frequency, which is very important for us. If we push the prism, it starts running like a quasi-particle. And finally, if we consider realistic models for metals, and we just started doing it just a few years ago with the means of very powerful molecular dynamic simulations. It's been demonstrated that prisms can be excited in metals. Here is our results modeling a discrete, standing discrete prism at 0K in alpha ferro. You see, nothing else is moving, just a few atoms, and it can survive in our MD experiments up to 400 of oscillations. Again, if you push it, it starts running in this manner, and then it hits a vacancy. It jumps away, and during this, it transfers to the vacancy, excites vacancy. Vacancy sitting in some of this potential wall will be excited, and this wall will start a little bit modulated. And there's a very simple formula which shows you that such modulation can result in a huge acceleration of jump from one well to another, which leads us to the preliminary conclusion number 1. Large amplitude oscillations of the dB atoms may result in a huge acceleration of chemical reaction rates. So the question is now whether the same can be true for nuclear reactions in solids. And my answer is yes. And here you see the palladium deuteride, how it's formed, and it results with this well-known rock-salt structure, which has been studied very thoroughly by Dmitriev and Gauthers, and they found that really, due to the difference of masses of palladium, any actually lattice like this, in particular palladium and deuterium, difference of masses results in this phonon gap indicated by this dashed line. Yeah? And in this phonon gap, we can excite the discrete prism. By external driving, or the nature by thermal fluctuations. Left picture shows you excitation by external driving, and it's a just stroboscopic picture enlarged by factor of 5 to become more visible of this central atom oscillating with a large amplitude. And the second picture shows you that its frequency decreases with increasing amplitude, and its energy 5 times exceeds the energy of the background temperature, and it's robust for about 100 of cycles. So, coherent and correlated motion of atoms within a discrete prism result in formation of coherent correlated states due to periodic calculations of parabolic potential wells for adjacent atoms. This is our model. And this results in the concept of Prism nanocollider, which greatly enhances the tunneling due to formation of these coherent correlated states. To understand why, we have to remind well-known and sometimes well-forgotten quantum mechanics. Well-known is the Heisenberg conceptuality principle, but not so well-known is that 3 years later, two gentlemen, Schrödinger and Robertson, independently generalized it, including the correlation between momentum and coordinate operators. 50 years later, Dadonov with Carruthers rearranged it and rearranging this in this nice form, which shows you that actually correlation can scale the Planck constant. It becomes dependent on correlation. So the more correlated is quantum moment, the higher is the Planck constant, and which means that the border between quantum and the classical world shifts, which means that uncertainty increases, and uncertainty increases, and with it increases the tunneling probability. And absolutely surprising, but absolutely strict result, I repeat it, the tunneling coefficient goes to 1 completely transparent barrier for practically any barrier height if the correlation is close enough to 1. Of course, the main question here, and it was asked this 30 years ago, how to realize this correlation. Then it was announced. Then, 4 years ago, Vladimir Vysotsky understood and demonstrated how to realize it. If we modulate the width of the well for the atom like this, it will result exactly, and it is shown again by solving the Schrödinger equations explicitly, it will result in enhancement of the correlation coefficient. The reason for it is, you see, the unperturbed well, we have this very narrow wave function and probability distribution. But for the correlation coefficient of 0.98, for instance, this green line shows you how it spreads, which means the probability to go under the barrier increases enormously. But important thing is that you can only do it if you modulate your well with the frequency either exactly corresponding to the agent frequency, self-frequency of the well, or approximately exceeding it, or double frequency. The second case is a so-called parametric resonance. In the first case, we have this oscillating correlation factor increasing like that steadily, and in the second case, it increases and increases up to the one in practically in several dozens of oscillations. Then, what we need to realize it on an atomic scale, we need a breezer behaving like that. The central atom vibrating with a large amplitude and some frequency, while his neighbors vibrate with half of this frequency in a coherent manner. At the first glance, it seems like it's rather not probable behavior of atoms. Whether it can be true, and here's the model that explains how it can be reached. It's based on examination of a density of phonon states for PDD. On the left is the one which is known from experiment. It has rather narrow phonon band between these blue areas. And in this phonon band there can exist a breezer, but his lower harmonic, this for adjacent atoms, they are stuck into the phonons, and so he doesn't exist long. But on the right, which is a hypothetical stoichiometric BDD in a strained condition with an increased phonon gap, we see that with increasing amplitude of breather, its frequency decreases, but the frequency of his neighbor decreases more strongly, and at 0.3 angstroms, the condition for parametric resonance is met. As a result, we can expect formation of coherent correlated states just in several dozens of oscillations. To be precise, hundreds of oscillations will lead you to the tunneling probability of 1 divided by 2, and he has 2 neighbors. That means that fusion can occur. So, preliminary conclusion is that large amplitude oscillation of these atoms may result in a giant increase of fusion barrier transparency, even for very moderate amplitudes of atomic oscillations, about 0.1 lattice space. And if the dB lifetime is large enough, and then we introduce the rate theory of formation of these discrete breezes. As a result, we have the plot, which compares the output power density versus current density. Yeah, I'm close now. And the dots are experiment, the curves are the model, with the parameters indicated on the table. The peaks mentioned from this experiment can be more or less easily explained within this model. Yes, and also important thing is that we've been talking about the electrolysis, but another driving force is the temperature, and increasing temperature, of course, increases excess power due to formation more and more breezers. It can be done under electrolysis conditions, but it can be done under ICCF conditions. And so, this, in principle, this approach, hopefully, will explain us how ICCF works. Well, of course, there are some fundamental questions remaining, but I will leave it probably for the questions, and then I might conclude. And thank you for your attention.
Any questions?
Very interesting talk. The lattice calculations. Most of the images look like they were done in a one-dimensional lattice. But in a three-dimensional lattice, one would expect the dissipation to be much faster from a soliton-like breather solution. Did you look at three-dimensional lattice as well?
Thank you for your question. Actually, that's what I've been doing for the last 3 years. And starting from the 2013, we have demonstrated, and this paper is already published, and now it's accepted by usual literary journals, where we model discrete breathers